Hello, my name is Samay Patel and this is my Physics 2011 Lab 4 about oscillations. So the goals of this report were to use the application tracker in order to observe and obtain data from the object attached to a spring, use the data from the application tracker in order to create a computational model for an object moving by applying Newton's laws and the energy principle, and compare and contrast between the experimental and computational model in order to determine the similarities and differences that occurred. So some of the concepts explored and some background information. As usual, we have used Newton's second law, which is the change in momentum over the change in time. Also, we have to understand the force of gravity, which is mass times 9.8 meters per second squared. Force of a spring, which is negative k L minus L naught times L hat, where L minus L naught is equal to S, L being the current length of the string and L naught being the relaxed length of the string. And the net force for this metal, which would be F net, is equal to F spring versus plus F grav, which are the two forces interacting in this situation. So continued, that was all about the forces. Now we have to go to the energy principle. We're here, since there's no change in energy, where delta E is equal to U of gravity plus kinetic energy plus U of spring. Delta U of gravity being potential gravity energy, and delta U of spring being potential energy of the spring. Delta U gravity is equal to m mass times gravity times height. Delta K is equal to 1/2 mv squared, and delta U of spring is equal to 1/2 ks squared. S being, the L minus L naught of the spring. So the procedure for this was obtain and upload a video of the object moving in oscillation with the spring attached. Once the tracker data has been obtained, create an experimental model using that data that was found. Use the provide glow script code, create a computational model for the object, then compare and contrast the models in order to determine major similarities and differences. So this was the video that I took of the experimental data. So that was the application tracker being used to record the spring or the object oscillating in a certain way. As you can see, these are the sinusoidal graphs up there. So some of the data continues. So the initial position of the thing on the graph was negative 0.0815, negative 0.660. As you can see, position is a vector in this case. Initial velocity, there was no initial velocity, it was 0. Mass of the object was 0.402. The period was the final timing minus the initial timing divided by 6, and each period was 1.552 seconds. The force of gravity in this case would be the mass of the object times the vector of gravity, which is equal to, there's none in the x and z direction, only in the y direction, negative 3.9396 newtons. And then we figured out, using the time period, we can figure out the spring constant from this using some basic algebra, with this being the time, the pi, mass. As you can see, the spring constant was found to be 6.60 newtons per meters. And then from this, since we know that there's no net force acting on the object, where mg and where gravity and spring are equal, we can also just use some algebra and determine that the relaxed length of the spring was 0.103 meters. So using the computational model, this was just the glow script code that was given to us, and I just changed it depending on my situation. Here's the mass. This was the initial position vector, velocity vector, timing, delta t was given to us. Gravity was 9.8. Relaxed length of the was 6.60. Relaxed length of the spring was 0.103. Now L, the position, is ball position minus spring position. L hat would obviously be this divided by the magnitude, and S would be the magnitude of this value minus L naught. And then obviously, these were the formulas that we just talked about: 1/2 mv squared, mgh, 1/2 ks squared, and then of course the total energy would be the addition of all of these. This is just the continued wild T's under this. Now we're defining initial energies. This is for the change in energies over time. And then this is the same way, the formula is 1/2 mv squared, etc., etc. So these were the comparisons. Obviously, delta E should be the same because there's no change in delta E. It is 0. And obviously from the experiment, the X position, we can see that the model had much less variation. And in this case, the model had much more variation in the experiment. This may have been due to some errors in the experiment. So what does this mean? Is the energy principle satisfied? Yes, if we look at the graph, we can see that the energy principle is satisfied. This can be seen because all the energies add up to 0 and energy is always conserved. An estimation of the oscillation periods, we can see that the x estimate and the y estimate roughly add up to around what our period was expected to be, but there's still some variations, probably due to some errors in the experiment. Thank you.